Hello guys, this is Prime Concept. In this video, I want to take a look at the studies under purely capacitive circuit. Of course, we've introduced the idea of AC circuit in our previous video, and we've looked at a purely resistive circuit that contains purely a resistor, right? Now, this time around, we want to consider a circuit that contains purely a capacitor. That is a purely capacitive circuit. So what is this circuit? It is a circuit that contains only a capacitor, or it is a circuit in which only the capacitive effect is pronounced. So it's a circuit that contains only a capacitor, and the circuit diagram is given like this. This is a symbol for our capacitor, right? Yes. Connected to our AC source, which is this. Is our current I, then our voltage V. So this is our purely capacitive circuit that contains only a capacitor. So that is a purely capacitive circuit. Now, what is one very important thing we want to know about the purely capacitive circuit? For a purely capacitive circuit, current leads voltage. Current is ahead of what? Voltage. For a purely capacitive circuit, current leads voltage by a phase angle of 90 degrees. So let me quickly write it. For a purely capacitive circuit, current leads voltage by a phase angle of, is either you say 90 degrees, because the equivalent of 90 degrees in radian is pi over 2. Pi over 2 radian is same thing as 90 degrees, or you can just say 1/4 of a circle. 1/4 of a circle. Remember that a circle is 360 degrees, right? One circle, one complete movement or oscillation or revolution is 360 degrees. So if you say 360 divided by 4, it will still give us 90. So any of these terms would still say the same thing. Now, is either you say current leads voltage, or you say that voltage lags behind current by a phase angle of 90 degrees. So any one of those terms would be correct. So it means that in this case, our phase angle phi is 90 degrees. So very important to us. Now, if that is the case, the next thing we want to point out is the phasor diagram. Phasor diagram, or we can call it vector diagram, a diagram that shows us the relationship between current and voltage and how one leads the other, right? Yes, in vector form. So quickly, if I make the x-axis my current, say the x-axis, which is the horizontal, if I call this my current axis, right? Then since we are saying that current leads voltage, it means that my voltage should be at this point. The voltage of my capacitor should be at this point. If I'm considering motion in this direction, then this would be the correct vector diagram when you say current leads voltage by an angle, a phase angle of what? 90 degrees. Now, in this specific case, I'm considering the horizontal axis. I'm considering the current as my reference. That's why I'm drawing current on the horizontal. I can still draw this in a different way. I can draw that differently by considering voltage as my reference. If I consider voltage as my reference, it means I will draw the voltage on the horizontal. I'll draw voltage on the horizontal. So remember, I'm still saying that current leads voltage. So if this is the case, it means my current should be facing up so that this statement will still be true. And current is ahead of this. This is our direction of motion by a phase angle of what? 90 degrees. So these two vector diagrams are saying the same thing, but I would prefer to always work with this, but I would always give both of them. Now, so this is what you need to know. Now, if this is the case, what is the instantaneous current and instantaneous voltage relationship for a purely capacitive circuit? The current, if you denote the current as the reference, as I naught sine omega t, this is our reference, it would mean that since my voltage is lagging, my voltage is going to be V naught sine omega t, then the phase angle by which it is lagging, I'm subtracting this. So this is what I would have as my relationship, right? Yes. And also, very quickly, we should know that for a purely capacitive circuit, from our Ohm's law relationship, the voltage across the capacitor Vc from that circuit I rubbed would be given as, okay, let's leave this till we mention the next quantity. So this is something that is important for us to take note of. Now, quickly, let's give the waveform. We have given, remember, we always draw two kinds of diagram: the phasor diagram, which is this, and then the waveform. So I'm going to draw the waveform for our purely capacitive circuit. The waveform is just a diagram that shows how current or voltage varies with time. So while our phasor diagram is a diagram that gives us the relationship between voltage and current. So say this would represent my current slash voltage. Now I can have that if my current is this, it would mean that my voltage would be lagging by this. And so on. So my voltage would be lagging by this. So it means I would call this first one current, call this second one voltage. So this length in difference, this length is what you actually call the phase diagram, and the phasor angle, that is the length in radian or in measured in angle, is 90 degrees, right? So I can continue this if I want. So I can draw it this way and so many other ways if I want. So that is my wave form for purely capacitive circuit. So you can see that current attains its maximum first, while voltage attains its maximum over a different or a longer time. So that's why we say current is leading voltage by a phase angle of 90, and that is why this is picking up from that side. So we want to look at the next important term under this, which is capacitive reactance. Capacitive reactance. Capacitive reactance is denoted by the symbol X subscript C. Right? Now, in a layman's way, or in a market woman's description, I would use that term. Capacitive reactance, you can just say it is the resistance of a capacitor. So in short, what I'm just trying to say is that capacitive reactance is actually resistance, but it is not the normal resistance, but it is the resistance that is provided or that is offered by a capacitor. That is why we call it capacitive reactance. I hope that is clear to us. So let's state it normally. So we can say capacitive reactance is the opposition. This is the opposition to the flow of current. In an AC circuit offered by a capacitor. So that is capacitive reactance. It is the opposition to the flow of current in an AC circuit that is offered by a capacitor. That is what we call capacitive reactance. And what is the symbol? X subscript what? C. Now, since it is a resistance, actually, it means that the unit of this quantity is going to be what? It's going to be ohms. So this is the unit. It is measured in ohms. Now, what is the relationship? So very quickly, we're going to take a short time to derive the relationship for capacitive reactance XL. Right? Now, if you recall, we know that current through an inductor and through a capacitor I is given by the capacitance of the capacitor. Remember, C is called capacitance of a capacitor, right? The V, the T. So this is the relationship for a capacitor. I is C, the V over what? The T. Now, if this is the case, you also know that we have mentioned that voltage is going to be, let's use a simple case, V naught sine omega t. I'm not going to use that relationship minus 90. So in this case, I want to consider voltage as reference. Then for current, it will be plus 90. So let's use this for simple case scenario. So I have that my current I is going to be C. Then I'm differentiating my voltage, which is actually V naught sine omega t, right? Yes. Okay. Now let me change this so that it would make sense. Or should I go this way? All right. No challenge. No challenge. Let's go. So we have this, the t. So this is what we have, right? Yes. Now we have that I is going to give us C. Now, if you differentiate it first, I want to bring V naught out because it's a constant. So I would have C V naught, then I'm just differentiating sine omega t with respect to time. I've brought V naught out. Now, when you differentiate, you want to differentiate sine omega t. The first thing you differentiate is omega t. When you differentiate omega t, you get omega. Then you differentiate sine, you get cos. Then you write back omega t. So quickly, I have that I is going to be what now? CV naught. When I differentiate omega t, I will get omega. Now, when I differentiate sine, I will get cos. Then I would write back what? Omega t. So this is what I have. So that if you recall, or better still, we can still write the standard form. Say that current I would be I naught cos omega t. This would be our current, right? Yes. So if we say that this is the standard form of the current, then it would simply mean that our peak current can be compared, right? So we can say that our peak current I naught would be this whole quantity. So we can just say that peak current I naught by comparison would be equal to C V naught then omega. So this is what we would have. So that I can write this. So what I'm going to do now is that I'm going to divide both sides by C omega. So divide by C omega, divide by C omega. So that this would go, this would go. Then I would have I naught divided by C omega equals what now? V naught. So same way I'm going to now divide by I naught. I'll just bring this down for simplification. So if I take I naught down, I'll be left with 1 here. So I'll just say 1 over C omega equals V naught over I naught. So I can write this. Now, so that you know that V over I actually represents resistance. But since we are considering a purely capacitive circuit, it means that the resistance in this case is going to be what? XC. So I can just replace this with XC. So I'll have 1 over C omega equals XC, which is our capacitive reactance, right? Yes, so this is our formula. So let me write it in a better way. So this is our formula. We can now say that XC, which is capacitive reactance, is just going to be 1 over C omega. And we know what omega is, right? Yes, omega is actually 2 pi f. So I can still write that XC subscript C is going to be 1 over 2 pi f C. So this is my relationship for capacitive reactance. So I've been able to derive this. So take note of this. Now, what are the points we need to know about the capacitive reactance? Very quickly, you would see from the relationship that the capacitive reactance is inversely related to frequency. So which simply means that when you decrease the frequency, you would increase the what? Resistance, the capacitive reactance. When you increase the frequency, you decrease the capacitive what? Reactance. So that when the frequency becomes 0, at the point where f becomes 0, then you would have that xc becomes what? Infinite. So under this condition, you say that this circuit, this purely capacitive circuit, would now begin to behave as a DC circuit. So first, you take note of this point, that when the frequency is 0, xc is infinite, it has infinitely large value, then circuit behaves as a DC circuit, even though it is an AC circuit, right? Yes, so you should also note that capacitive reactance is inversely related to the frequency that we have mentioned. So what will be the graph that relates XC and F? It's very simple. I can show this graphically. If I call this XC and call this the frequency, it means that this graph of this against this is going to be a curve. So it's going to be like this, like this. So while this is increasing, this one is decreasing. Or while this is decreasing, this one is increasing. So this is what you have as the graph of XC against F. So very quickly, before we round off this video, we're going to take one simple problem. So let me drop the problem on the board. Alright, so let's take this quick example and then use it to conclude this video. Now the question says an alternating frequency of 50 Hz. So they gave us the frequency. Of course, you should know that frequency actually talks about number of oscillations with time. So frequency tells you how many oscillations you have in 1 second. The frequency tells you is actually the major quantity that describes AC circuit, the oscillation. So 50 Hz, it's connected to a capacitor of 100. So the capacitance of that capacitor is 100 microfarad. So take note of the micro. So one of the first things you want to do is to remove this micro. And how do you remove the micro? You introduce 10 to power minus 6. So I would have 100 times 10 to power minus 6, then farad. So that's the first thing you want to do. Then across a PD of 12 volts. So the voltage supply is 12 volts. Now calculate the capacitance of the capacitor in ohms. So what they are just telling us is to calculate the capacitive reactance, because that is the capacitance of the capacitor measured in ohms. So they want us to find XC. We know that the relationship for XC is XC equals 1 over 2 pi f then C. So we have that XC is going to be 1 divided by 2 pi. Let me use pi as 3.14. Then times my frequency, which is 50 Hertz, times my C. My C, now let me write this. This is going to be 1, 2. So that is going to be actually 10 to power minus 4. That's what it will be. So this is equivalent to 10 to power minus 4 farad, right? Yeah, because 100 is 10 to power 2. 2 minus 6 is minus 4. So if I punch this, I would have 2 times 3.14 times 50. So this would give me 314. So quickly I would say 1 divided by 314. So I have 1, 2, 3. So I have 3.18 times 10 to power. When this comes up, it becomes 4. 4 minus 3 is 1. So I can just say this is going to be 31.8 ohms. So that is what I would get as my capacitive reactance, or my capacitance measured in ohms is this. So you would notice that we didn't need this, right? Yes, so we're assuming they wanted us to calculate the current flowing through that. Then we would now need this voltage. So they want you to calculate the current. You would now see that the current is going to be the voltage V, because that is the only source. Then V divided by XC. So you want to find current, you just say 12 divided by 31.8. So with this, you can get the current as an extra quantity. 12 divided by 31.8 would give us 0.38 ampere. So I believe that this whole concept we've analyzed is very clear to you. If you enjoy my videos and you value my content, please do well to subscribe if you are yet to subscribe. Like every of my videos when you come across them. Comment on my videos. Tell me what you want me to do next. Then share this video with 10 of your friends. Tell them it is prime concept. I'll see you in my next video. Thank you.